What I've detailed in the handout, what I'm going to talk about, is a logical approach to fault finding. It may sound as though this is going to be a rules, Ian Batty says therefore you must. My attitude is, once you know the rules, then you can make decisions about how rigidly you should apply them, and whether you even need to go in the order that's suggested in the fault finding process. If you don't have a very good understanding of how all these rules work, my recommendation is you follow them through step by step. You'll get familiar with the entire fault finding process, with how to think about stuff and how to do detection, analysis, rectification. And you'll get confident, and then you'll be able to say, okay, I understand why he said to do it this way, but I've got my own particular approach to doing things. So, I've picked 3 Mantel radios because they're probably the radios we've got most access to and we're most familiar with. Be aware that this fault finding process will work from anything from one transistor radio through to, oh, I don't know, a flying bomb camera from 1945. It's the same, true story. It's the same process. All you need to do is adapt it to your own knowledge and to the type of equipment and level of complexity that you're working on. So, let's start. I reckon, here's the process. Know your beast, safety and visual inspection, symptoms, power up, DC conditions, AC and signal conditions, and there's just a few more things. You can get information, and thank you to Kevin Chant for his excellent website. If you do pop onto Kevin's website, please send him a thank you email, because the amount of work he's done is just completely outstanding. He's got Australian transistor radios, he's got Australian valve radios, transistor radios. He's also got car radios. You've got TVs as well, Kevin?
Yeah, starting to increase that.
Okay, so Kevin has done a magnificent amount of work. It's available, it's online, it's free, it's as close as your desktop and your printer. But like I said, if you do use it, give Kevin a vote of thanks, because I reckon it's a pretty outstanding effort. If you don't find anything on Kevin's site, you may be aware of the books that Philip Lay put together. This particular one has a whole lot of Astor circuits in it. I'll probably mention it again, but what Philip's managed to do is get pretty much everything in hard copy. He's got sets that were issued before the ARSMs. It's got sets that are not in the ARSMs, and it's got sets that were released after the ARSMs were discontinued. So if you've got the ARSMs, that's good. If you can't find something in there, then very possibly you'll find it in the Philip Lay books. There are 10 of them, and one's still in preparation. If you want to find out about them, go onto the HRSA website, and I think it's resources, and then you'll be able to find circuit books, and there's a long searchable list for each particular volume. So you can find the particular set you're looking for, volume, page number, and so forth. If you're still not doing any good, Ernst Erb's Radio Museum used to be subscription only, but I think you can now get what, 1 or 2 or a few a day. Is that right, Kevin?
3.
You can get 3 a day, okay. So if you're after more obscure European sets that neither Kevin nor Philip have captured, then head off to Radio Museum. And then finally, if you can do no good at all, get onto our own circuits manager, Bruce Wilkie, and you'll find all of this information. I think it's page 2 or 3 of Radio Waves. It's in one of those information panels, along with all the office bearers. So you should be able to get the information you need, and I'll talk a couple of times about why that's important as I go through the talk. Okay, safety and visual inspection. I have on my workbench a Variac and an AC watt meter and an isolation tranny. The AC watt meter is important because if you start to bring the set up and find you're getting a lot of power consumption, more than about 30 or 40 watts, there's something wrong with the set. You should stop there and find out what's wrong. And the safety, really, thank you to Marcus Chick for sending that one in. I don't feel lucky enough to even think about doing anything with that set until I've rectified that mains entry. And oh, by the way, that's 240 volt cable. It's not like 12 volts or anything. I recommend you use a cord anchor. It's a two-piece grip, and it grips the cord and prevents it from rotating. Ideally, it should go into a slightly D-shaped hole to stop it twisting, but an ordinary tight hole, I've found they won't twist. So it's completely secure. It stops the cord from pulling and rotating, and as well as that, you may be able to see that the leads break out immediately inside the chassis. You can use a grommet and a chassis clamp. That works fine, but then you've got an amount of cable that you can't really pick apart and route anywhere inside the chassis. If you've particularly got a tight chassis, then that's the ideal solution, because as soon as it comes in, the leads part out and you can dress them to where you need. They're available from JCar and heaps of other places. I strongly recommend that that's your method of preference. Some sets actually, in the cord hole, they have a rolled edge, which is considered safe. It's still not my preference, but if you have a set with that, then I'd probably leave it, but make sure the cord clamp is secure so that the cord can't pull or rotate. Okay. Didn't have any symptoms. This was a set I bought, I think at an auction, had no idea what was going on. So popped it on the bench into my Variac wattmeter, powered up. What did I get? A bit of hum. That was all I got out of the darn thing. DC conditions, low HT. Now, this Mickey is unusual, and it uses an HT of only about 150 volts. It was originally an AC-DC set, which worked with fairly low HT, and they kept the basic design. So although the 140, 150 seems low, that's what it's meant to be. So here's Know Your Beast. You look at an HT of 150 and you go, it's rubbish, I've got to pull it apart and start over. Nope, that particular set works fine just like it is. But I did find the first filter capacitor wasn't even there. The second one had been replaced with a new one. The first one, there, who cares? So the first thing I found was the first filter capacitor, which is C22 on the circuit, wasn't even there. So putting that in brought up the HT to what I expected it should be. Added first filter cap. Then I found I had low back bias at the output grid. And that was another discovery, because some sets will use individual cathode bias for each stage. Some will use back bias for all signal stages, converter, IF, output, maybe the audio. Some will use cathode bias, some will use back bias. So what had also happened was the previous repairer had put a large paper filter cap in the back bias line, and that was upsetting the back bias as well. There was a filter cap in the back bias circuit, which is this fella here, and that was leaky. Now, normally a slightly leaky paper cap wouldn't matter that much, but in this circuit, where you've got 470k to 50k high resistances, its leakage was pulling the back bias down quite a lot. How much bias should you expect? This is it's a 43, which is the UX version of the 6F6. That entire class of valves, the first lot of pentodes, tetrodes, need about minus 20 volts on the grid for normal operation. The ones that followed, the next generation, the 6V6, use about minus 12. And the final version, the EL3, the 6M5, and those more modern ones use about minus 6. So what should the grid bias be? Well, if it's not indicated on the circuit, off to the valve data book or the circuit diagram and find out what it should be. In this case, it should have been about minus 20, and it wasn't. But repairing that fault in the bias circuit fixed it. Got the back bias working? Okay, so I had my DCs about right. How good is it? At the output voltage grid, at the grid of the output valve, you expect about 1 volt of signal to give 50 milliwatts out. So 50 milliwatts, if you don't have a wattmeter, how do you do that? Pretty simple. Get yourself an AC voltmeter, your multimeter, digital or analog, 0.1 microfarad capacitor, anode of the output valve to ground, sorry, anode of the output valve to the meter to ground. For 6V6, 6L6, all of them, you expect about 15 volts at the anode for 50 milliwatts. The actual value doesn't matter, but 15 volts is about right. If it's a battery valve, such as a 3S4, 3V4, you need about 20 volts at the anode. Again, the actual value isn't that critical, but set yourself a voltage that you reckon you should be getting, and as long as you're getting that consistently as you're working, you know that the set is coming good. So, 50 milliwatts out, I had about a volt of signal on the output grid. That's fine, it was working pretty well. This is a fault I inherited from another set, but I had a set that came up pretty well, but as soon as I turned up the volume, I got a lot of distortion. It turned out that the filter cap, or the bypass cap on the screen grid of the first audio was leaky and it was pulling the screen voltage down, which was reducing the anode current, of course, and therefore the valve was overloading very rapidly. So in this circuit, although there's no screen bypass, the fault would have been revealed around about on the 6B7 grid. You may notice that the voltages in this circuit are pretty low, 38 volts at the anode and then 19 at the screen. Looks wrong, but checking on the circuit, that's exactly what it's meant to be because it's working from quite a low HT. The circuit still gives heaps of gain, it's just that those voltages are unusual. Again, know your beast, don't take fright at abnormally low or high voltages from what you expect because the circuit may be working perfectly, and this one was. Okay, about 25 millivolts on the volume control. It just happens that for any radio of any kind, valve or transistor, if it's got two amplifying stages, a Mantel set with a 6B7 and a 43, or a transistor set with an OC71 and two OC72s, two stages, somewhere between about 10 and 30 millivolts should give you your 50 milliwatts output. Now that's going to vary from set to set, but back of the envelope, if I can put about 10 millivolts to 30 on the volume control, turn it up full, I should get my 15 volts or 50 milliwatts at the output stage. And it's working pretty well. That's about what I expected. When I went right back and checked everything, that was the correct value. Okay, so this is a 5-valve Mantel, but it was designed in 1930 something, and yeah, well, stuff was pretty rubbish back then. I needed about 200 microvolts of signal at the antenna at the top end. Well, all right, if that's true, why do I need not much more than 20 microvolts in the middle of the band? Like that's a 10-to-1 difference between mid-band and the top end, and a lot of sets actually get more sensitive as you get towards the top end, right? So what's going on there? Yeah. And as well, the low sensitivity was what, about 1/6 of what it should be, so it's obviously something really wrong in the circuit. Now, the first thing I thought was, it's the IF. Well, no, because the IF doesn't depend on the signal frequency or the tuning, so it has to be somewhere in the converter circuit. I checked the alignment, it was okay. Then I went around and checked the antenna circuit, and here's what I found. You may be familiar with this little fella. It's colloquially known as a gimmick. It's correctly called the top coupling capacitor. The problem we have with the usual antenna transformer is they don't perform so well towards the top of the band. So what designers do is they pop in a small capacitor, it's usually about 2 to 5 picofarads, to bring up the gain at the top end. So I looked all around the circuit and I went, oh, I've got to shorten the antenna circuit. Well, no, because it was tuning. Well, maybe I've got something else happening. The gain was not shorted. The antenna coil secondary was 10 ohms or something. The primary was about the same. That capacitor was okay, that capacitor was okay, that inductor was okay. This capacitor was shorted. And that was completely wrecking the tuning of the antenna circuit. So I looked in the Mickey, And in this set, they've got two short bits of their hookup wire twisted together and with a bit of friction tape on top to hold it in place. That's all right. So I took the friction tape off. I think it was the first time it had ever been off. And there were the two wires with the conductors twisted together. So the capacitor was shorted, and rather than giving just a little bit of extra boost at the top end of the band, it was completely wrecking the entire tuning of the antenna circuit. Out with the cyclos, clipped off the bare wires, repositioned the tape so nobody would know, and it was improved. The sensitivity was better, but, what's wrong with this picture? Well, it's a bit better at mid-band. It's still pretty rubbish up the top end where it commonly gets better, and it's still pretty bad at the bottom end. So now what's going on? I reckon I'd been through this circuit pretty thoroughly. I'd done every test, every measurement I could think of. There was still something wrong. It wasn't performing with a fairly even sensitivity curve across the band. So I looked at I'll just go back to where it is. I looked at the IF filter, which is that inductor and that capacitor. Now you'll find some sets, particularly in the 30s, maybe into the 40s, that use an IF filter, which sounds odd because no one's running around transmitting on the intermediate frequency of 455. But from the 1920s through into the 1930s, marine radio communication used allocated frequencies, so everyone knew they were legal and in existence, around about 400 to about 460 kilohertz. So that filter was there in case there were marine transmissions in the neighbourhood. In fact, one was 454 kilohertz. So that filter was there not to suppress what we think of as IF, but to suppress marine radio transmissions. So I looked at that and well, that's the only thing that's wrong, surely. So, got out the side cutters and took out the filter and applied the signal directly in to C2, the 0.001. That's better. I've now got a sensitivity better than 10 microvolts at 600K. I don't know if you're as fussy about signal levels and stuff as I am, but I've said to a couple of you already, that is the second best Mantel radio for sensitivity that I've tested ever. So in the mid-1930s, Astor, who we think of as a sort of cheap Mantel sets, designed what I consider to be one of the best radio designs ever. There's an article in Silicon Chip, June 2021, that goes through the complete design description. But if you've got a Mickey, particularly one of the OZs on the shelf, you've got an exceptionally good radio. You may decide to bypass that filter, or you may prefer to leave it completely original. But just be aware that the completely original, the original factory design set doesn't take full advantage of the design. When I first looked at the Mickey, I thought, oh, come on, if you've ever looked at one, I think what happened when they made them is they got the chassis, and one team of people bolted all the stuff on top of the chassis, the speaker, the powertrain, yada, 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 and the gang. Another lot put the sockets in, another lot tipped the tub upside down, got a bucket of parts and threw them in, and that went on to the soldering station where people just soldered everything to everything to everything. It really is, as far as working on, pretty much a mess. But the actual electrical design is an exceptionally good radio. You can tell I'm a fan. And just to refresh, the red curve is what happened with that, what I believe is a factory error of the gimmick capacitor being shorted. The blue line is their original design, which I consider to be faulty due to that dodgy IF filter. And the third line shows that this is an exceptionally good radio, and it's Australian. So, a couple of things. Firstly, I was uncertain about the biasing in this circuit. This particular radio, I'll just skip back to the circuit. Sorry. This particular radio is a bit unusual. Where are we? It's back bias on the output stage and on the first audio. Yeah, that's negative. That's negative. Output stage, first audio use back bias. The two signal stages, the converter and the IF use cathode bias. Other issues use back bias for the whole thing. Others use a mixture of cathode bias, back bias. I was stuck with having to trace out the actual circuit to discover what had happened. I was speaking with Jim Eason about the circuit books. Philip Lay has gotten just about everything you can possibly imagine. I did find in, which one is it? It's book 11. So there is a description from Astor of this mixed bias and cathode bias circuit. And you can see the tabs I've put in to find out all of this stuff and where it is. So again, a boost for these books. They not only have the circuits in quite good condition, they also have factory notes, release notes, modification notes, which are pretty hard to find. Are you able to find them, Kevin?
Quite a lot of the Astor stuff, yes.
Oh, good, okay. So there is more than just the one source, but be aware that you may need to do a lot of digging, either do your own hand tracing to discover what the circuit is, especially with these older sets where they did revision after revision after revision in the one model, or see if you can find first how peculiar your set is, and then whether you can actually find a reference book. Worst case, you're actually going to have to trace the whole thing out by hand and tidy the drawing up so you can start using it. And again, worst case, you're going to have to work out what the voltages ought to be. And like I said with this one, don't be fooled by the low DC voltages on that 6B7, because that's what they're meant to be. You'd usually expect something about, half HT for the first audio's anode, and about about 1/3 for the screen. In this particular case, it's not so. Wait a minute. Has anyone got questions or comments? Kevin?
With the circuit diagrams
Yep.
and the modifications we talk about Astor, if you look at, say, a Chrysler 11-4, that's a beehive, 34 revisions. So 34 different circuits.
34, okay, so Kevin is telling us that, which brand was it? The
It was Chrysler.
Chrysler, and which model?
11-4 beehive.
The 11.4 beehive, and how many was it again?
34.
Come on, 34 revisions.
Found today.
Gosh.
And some of those are from just resistor values right through to the change between electrodynamic speaker to PUMAG. So some major modifications, all in the same case, all model 11.4s. But yeah, 34 revisions I've found on that one so far.
Okay, so that's a very good example to know your beast. You may look at things that don't appear to be the standard circuit and say, hey, who cares? I would want to be as sure as I could that what I have on my circuit diagram matches what the actual as-built set is. So be aware of that, and I'll just refresh that. Kevin's found that particular beehive with a lot of different revisions, and they could be important ones, like you said, the change from an electrodynamic speaker to a permanent magnet speaker. That would have important implications for the circuit design.
The Astor GMs were in that transition phase where they went from all octal to part octal, part miniature, to all miniature over their production life. So you find slightly different circuits, different valve bases and that sort of stuff. So yeah, it pays to pay attention, I guess, when you're working on them to get the right information.
Yes, and I guess even if the actual, all the circuit values are similar, there's a big difference between a 6SQ7 octal duodiode and a 6AV6 miniature 7-pin duodiode triode. The actual function is pretty much the same, and you may even find the same circuit values, but their pinouts are completely different. So you do need either to get the as-built circuit, or worst case, if you've got a 6AV6, you can get nothing that shows it. It's out to the valve book and pull out the pinouts out of the valve book, and then at least you know where to take your measurements. Yeah. Anyone else? Yeah.
I don't know, maybe it's just me. I tend to get a set and I measure all the resistors and check all the transformers and find out anything that's working or not working first. Whereas you seem to be plugging it in but at low voltage and then wind it up to find whether it works or not. Got any comment on that?
Yes, I guess what I call it, I take a sort of operational approach. And just to take that point of power consumption, what I'll do is I'll pull out all the valves and then put it on the tester. Sorry, pull out all the valves except the rectifier. Sorry, I'll pull out the rectifier and leave the other valves in. Okay, that's what I meant to say. Then put it on my test bench and bring it up. I haven't got the rectifier in, so there's no risk of electrolytics exploding. I'll bring it up and I should get maybe 20 watts of consumption or less. If I get much more than that, remember this is just the power transformer and the valve heaters. If I get a whole lot more than 20 watts power consumption, I know I've got a fault and it's most likely the transformer. If the set passes that test, I'll leave it on, check it every couple of minutes, leave it on for maybe an hour or so. If the transformer's still just warm to touch, everything's probably okay, and if it had absorbed a bit of moisture, it's on its way to drying out. Okay? Turn everything off, power down, pop the rectifier in, and then bring up the power. I've got a slight refinement on that because what I usually do is I've got a 0 to 400 DC supply. So I'll power the heaters through the powertrain, but I'll leave the rectifier out while I'm in this testing phase, and I'll bring up the 400 volt power supply. And because that's metered, I instantly know whether I'm getting excessive drain due to faulty electrolytics. You can expect the power consumption or the current into the HT of a 4 to 5 valve mantle to be somewhere about 40, maybe 50 or 60 milliamps. If you get a lot less than that, my immediate suspect is the output valve's dead because it draws most of the power. If I've got a lot more than that, my immediate suspect is the capacitors. So I've got I guess a cautious approach that gets me to the power supply not exploding and hopping off the bench. As far as measuring resistors in detail, I tend not to do that because what I rely on is if the valves are okay and if all the DC voltages are okay, I'm going to scoot through and assume that the resistors are okay. But that's my particular approach to it. And what you're doing, you're actually certifying every component, and you can be quite certain that as you go through and do your measurements, you're discovering faulty components, which my method, I would have to go through, find a DC voltage was wrong, and then deduce the fact that some of the resistances in the circuit were crook. So it was horses for courses. And like I said, I've got my preferred method, definitely works, but you've got a different, more investigative method, and that will also work, and it probably works just as well.
It takes more time.
Yeah, but you managed to actually certify all the components.
Well, I check the circuit as well at the same time.
Yeah, yeah. And you're not left with finally putting the set on the bench, giving it the full test and going, it's still not right. So you do actually...
Micros or something like that, microcapacitors.
Yep, so I call capacitors our ancient enemies. Electrolytics dry out or go leaky. Paper capacitors go leaky, and by the way, you can't reform paper caps. They just never do. Microcapacitors are considered to be pretty reliable, but they can actually grow, the silver micro ones can grow silver whiskers or dendrites within the package and give you minute shorts. And I remember a member saying he'd had a radio where the bypass capacitor from the first audio to ground to filter out the IF was intermittent. He was getting a crackling sound coming through the audio. So microcapacitors are usually okay, but they can have that intermittent failure. Ceramic capacitors are usually okay, but those little red tip ceramic capacitors they use in transistor radios, I have found some of them to be leaky. And I got a shake of the head there. Yeah.
I agree with you, it's right.
Okay, so its capacitors are the most suspect. I was going to talk about recapping, but I'll do it now. Some people just go, going to recap. And I understand that because what you've done is you've replaced the components that are most likely to be faulty. And some people will go further, they'll get a new kit of kit of new valves or valves they've tested, dyke out all the old ones and put in new valves. And they know that they've removed the components most likely to cause faults. I've got a more sort of, back to front approach, so I don't tend to do that. The advantage of recapping is you know that you've removed the most likely component to be faulty. No, you haven't, because I had a Astor Aladdin, the vibrator set, the 6-volt one, where everything was working just fine. A couple of capacitors were replaced and that was all right. The AGC wasn't working. Traced around. Finally, I found that the AGC line going into the first IF was shorted to ground. And the reason it was shorted to ground was there was a trimmer cap inside it where one end of it should have been above ground so that the AGC could enter the can. It was shorted to ground to the adjusting screw. That can had never been opened, so it was actually a manufacturing fault. So I agree with the idea of recapping, but there's some capacitors you're probably never going to suspect. So the reason I don't tend to recap is I don't know how long it takes to recap a radio. I reckon it's a good morning's work. For a set such as the Mickey, if you've had a look at the underside of them, it's a complete dog's breakfast. I don't know if you could do a recap without stripping it back to sockets, because there are so many components overlaid and in such inconvenient positions. So I guess I'm a bit conservative. I also look at the labour of doing a recap, and also the more work you do on a set, I guess my worst case analysis is the more likely you are to mess something up. But again, that's a matter of each of us having an individual particular strategy. So recaps, if that makes sense to you, yes, you know you've probably eliminated, well, you have eliminated the most suspect component as a possible cause of failure. Yeah.
At a minimum, I always change the coupling capacitor to the output valve, because that's what will take out your output transformers.
That's got to be just about every time, hasn't it?
As an insurance policy, regardless.
Okay, and that's wise, because so often, in fact, I think I said ages ago, if you replace one component, coupling cap from first audio to output valve, you'll fix half the sets. So yes, and that circuit is very sensitive to leakage, because there's a high value grid resistor on the output valve, and it doesn't need any more than a few microamps to pull that up and completely mess up the bias. So yeah, that coupling cap is definitely a suspect.